So previously we've said that capacitors can store charge, which they can later release as an electrical current. So they can effectively act as a battery for a short period of time. So this means that they are storing energy. So what we're going to do now is calculate how much energy a capacitor can store. So in order to do that, let's consider a very simple capacitor, just a parallel plate capacitor such as this one shown here. Now initially, our plates are completely uncharged and they're separated by a distance d. And now what I want you to imagine doing is moving small increments of charge, dq, from the left plate to the right plate. So as we move those positive charges away from the left plate is going to become negative, and when they arrive at the right plate is going to become positive. So imagine that we do this for a short period of time until the left plate has a charge of minus q and the right plate has a charge of plus q. Now what we're going to do is work out how much electrostatic work is required to move the next increment of charge dq from that left plate to that right plate. So the increment of work, dW, is equal to the integral of F dot ds, and the force in this case is the electrostatic force. So this is given by dq times E. So we can write this as equal to dq times the integral of E dot ds. Now in this case, we've got the electric field between parallel plate capacitors, which is just equal to sigma over epsilon naught, which is q over a epsilon naught. So we can write this integral as minus dq, and then we've got our integral going from 0 to d, because that's the separation between our two plates, of q divided by a epsilon naught ds. None of these are functions of s, so when we integrate this, we end up with minus dq times q divided by a epsilon naught and then s evaluated at 0 and d, which is just equal to minus dq times q times d divided by a epsilon naught. Now, because this is a parallel plate capacitor, we know that the capacitance is given by epsilon naught a on d. So we can write this as dw is equal to minus q on c dq. Now what we want to do is calculate, well, what's the total energy that we need to add to charge it up to some final charge, say capital Q. So to do that, remember that the change in potential is negative the electrostatic work done. As when we're moving against the electric field, we're doing work on the system, so we're adding potential energy to the system. So we can write, well, du is equal to q over c dq. And now we're going to integrate this to work out the total potential energy to charge up to Q. So the integral of du is just U, the total energy, and that is equal to the integral. And we're going from a charge of 0 to a charge of capital Q, and then we've got Q on C dQ. So this is equal to 1 on C times Q squared on 2, evaluated at Q and 0. So this is equal to a half Q squared on C. Now there's a few different ways we can write this if we remember that C is equal to Q on V. So we've already seen that U is equal to half Q squared on C. We can also write it as a half CV squared or as a half QV. So let's have a look at an example problem now.
So the question is, a flash on a camera uses a 100 microfarad capacitor charged to a potential of 250 volts. When the flash is fired, the capacitor discharges in 1 millisecond. How much energy is stored on the capacitor before it discharges? What is the average power used by the flash when it is firing? Okay, so to work out the energy stored, we're going to need to use our equation U is equal to a half Q squared on C, which we can also write as a half CV squared, which is also equal to a half QV. Now, in this case, we're told about the capacitance and we're also told about the voltage. So it makes sense to use this second one here where we have the capacitance and the voltage. So we can write, well, U is equal to a half CV squared, and then we can just substitute in our numbers. So we've got a half times 100 microfarads times V squared, which is 250 squared. And solving that on the calculator, we get 3.125 joules. And then since everything's given to two significant figures, let's write this as 3.1 joules. And then next we're asked for the average power used. So the power is equal to the energy over the time. So we've just calculated the energy, which is discharged, 3.125, and we divide by the time, which is 1 millisecond, so 1 times 10 to the minus 3. So solving this, we get 3,125 watts. So this is equal to 3,100 watts to two significant figures.